Hello everyone and welcome to the 45th lecture of the course Advanced Structural Analysis. We have started with the discussion on the geometrical nonlinearity, and with this session we will try to introduce the basic matrices of the geometrical nonlinear system. The approach which we will try to cover in this session will include the incremental stiffness form and then the standard stiffness expressions for the geometrically nonlinear system. So, we are doing this problem from the reference of a plane truss. So, initially we have considered that the standard material which is considered is having the true translation at both the ends. We identified the given material or the given member in the generalized member coordinates. So, the structural coordinate could be a completely different in a different orientation, but we are first identifying the member coordinate and locating its complete stiffness parameters at the beginning, and once we are able to do it, then we will try to modify the system stiffness to the generalized global coordinates. So, to start with the process, we have done in the last session the evaluation of the general strain displacement relationship which connects the change in the length in the given member with respect to the nodal changes in the displacements of the given system. So, we must understand that del u bar are the nodal displacements which are the amount of the displacement at the nodes of the given system, any small changes, whereas del of E is the change in the length of the given member, which is the internal length change of the given system, and it is connected with a parameter of A which we have written in terms of the parameter of phi, which is defined as the kind of rotation of the system, which is itself a function of V displacement. So, we can understand that this overall expression is a function of displacement, or someone can also write in a general form that E, which is the change in the length of the member, is equal to the function of the displacement. So, this typically identifies one basic idea that any change in the length of the system is now no longer a constant value, but rather it depends upon the amount of the nodal displacements of the given system. Now, with this idea in mind, we move to the second equilibrium condition. We define the amount of the nodal loads which are active in the given system in terms of the internal member force on the given system. So, S was the internal member force. If we consider that this is the member, so this was the force in the deformed configuration of the system, whereas P bar refers to the amount of the loads which are active in the direction of the nodal displacements of the given system. So, the nodal displacement as they are defined in the initial member coordinate. So, we define the member forces as well in the given system in this member. So, these are the values of P1, Q1, P1 bar, Q1 bar, P2 bar and Q2 bar in the given system. So, we try to correlate these values of the loads in terms of the internal member force of the given system, and this is again connected with the same A vector of the given system which we have identified. In terms of the systems where the number of member forces are more, like in a truss member there is only one axial force. So, that is why we are just connecting it with respect to a simple row vector like this. But in cases where there will be more than one forces in the given system, like we will see the problem of the beam later on, we identify that the A can also become a general matrix of the given system. In the similar manner, finally, we identified the material constitutive rule, and through that we were able to define the small change in the member forces in terms of the nodal displacements of the given system. So, the basic idea of the whole approach is that we try to define the basic relationship of the kinematics, equilibrium and the material constitutive rule of the given system, and we try to express everything in terms of the displacement parameters of the given system. So, if you look at the equation 2 also, we identified that P bar is equal to A transpose S, and now as we have already converted S as a function of displacement of the given system by this equation 3, so we realize that this force value itself will be a function of the displacements at the nodal values of the given system. So, we start with the process using the similar equation. We consider that this is the equilibrium equation which is identified for the given system, and now we can take up the small fractional changes in the given system, which means that if initially the system is considered to be having these nodal forces corresponding to the identified displacements, we can consider that for any small change in these loads, what are the displacements which are getting in the given problem. So, it is a relationship between the d of P bar, which is the small change in the displacement, and the d of u bar, which is the change in the displacement of the given system. So, as we change the amount of the force at the nodal points, how the displacement modifies, that we typically want to identify from this given process. So, as we have this equation identified, we write it further as dp bar can be written as the small change in terms of the expression A transpose S. Now, as we understand that if we are going with the small changes with respect to A transpose S expression, if the A transpose is a constant value, the expression will simply move to d of S parameter like this. But as we understand that A itself is a function of the displacement of the given system, and all these derivatives, the way we are identifying them, they are with respect to the displacement of the given system. So, we understand that this can be written as dA transpose S in the given problem. So, it is a simple relationship which we define in a simple manner, like d upon dx of expression A into B. If both are function of x, we simply write it as A into dB upon dx plus B into dA upon dx in the given problem. So, using the same idea, we are adopting this given change. Only thing is that rather than writing d of dp by dx explicitly, we are or dp by du explicitly in the given system, we are identifying the small changes first at the given system, but the intention is to get these changes in terms of the variable quantities of the given system, which are the displacements at the nodal positions. Now, once we have written this incremental change in the stiffness, we get here two expressions. Say this is the expression 1 and this is the expression 2 of the given system. We take one by one both the expressions of the given system. So, as we go with the first expression, we write it as A transpose into ds. Now, as a A transpose value, we have already obtained the value of the A parameter. We obtain the d of S, and if we write the d of S parameter from this equation, we write it as ds is equal to k naught A into d of u bar in the given system, which means that now the parameter of the du bar has been introduced in the given system. The left hand side of the equation which we initially started with was containing dp bar, and I will now identify, if I just substitute the first part in the equation, I will write it as dp bar is equal to A transpose k naught A into du bar in the given system, this as a one part, plus the second part we have not solved as of now. So, I will just keep it as it is, dA transpose into S in the given problem. So, what we realize that if this is the load increment in the given system, this is the displacement increment in the given problem. So, this is supposed to be the parameter of the stiffness in the given system. So, we identify that this is the parameter of the stiffness which we describe again in the local coordinates of the given system, and this is the stiffness which is identified with respect to the terms which are included in the A vector of the given system. So, if we just now look in the method, the overall terms of the system, we can see it as that k bar can be located as A transpose k naught into A. A transpose if we define as a value, so we have already seen that A as an expression is written over here. So, if I just substitute this value, it appears as the standard vector 1 minus of phi 1 phi. K naught in this case is a constant value which is AE upon L for the given system, and then we multiply this with the A value again, which is 1 minus of phi 1 and phi in the given system. So, the idea is that once I do this multiplication of the given system, this is a vector which is containing a 4 cross 1 size. This is also a vector which is of the size 1 cross 4. This is a constant value in between. So, if I multiply these two matrices, these two vectors, I will eventually end up with a size of 4 cross 4 vector or 4 cross 4 matrix in the given system, which means that the 4 amount of nodal displacement values which are identified, they will be related to 4 displacements at the nodal values, and of course, that is what we realize, that this has to be connected with the 4 cross 4 matrix, and that is the 4 cross 4 stiffness matrix of the given system. So, now we want to evaluate this stiffness matrix of the given system first. So, as I write here that k bar is written as minus of 1 minus phi 1 phi, then the A upon L I can just take as the common value as k naught in the given system, say this is a constant AE upon L value, and then I multiply with the second vector which is minus 1 minus phi 1 and phi in the given system. So, as I multiply these systems, it's a 4 cross 4 matrix which I am eventually going to get, and I just multiply that to write it as, and it appears as 1, the first multiplication 1, then phi, then minus 1 minus phi, then phi square minus phi minus of phi square, then similarly minus 1 minus phi 1 phi, and over here I can write it as minus of phi minus phi square phi and phi square. So, these are the multiplication values which I just get after multiplying these matrices. What it eventually mean, if I now break this system into two parts, I think this we need to just understand that k naught can be written in this system such that I first take only the constant values of the given system, which are 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 and 0 0 values of the given system. So, what we did over here, from this given matrix which was identified, I just took the constant values first and those are separated from the system. Then I took the remaining values which are except the constant values or the 1 unit values of the given system, and if I arrange those values I get it as 0 phi 0 minus phi and similarly over here 0 minus of phi 0 phi. Right. So, this is what we have got eventually by doing this whole calculation. So, I will briefly show it now, because we have just done the calculation to recall it all what we did. We started with the incremental change in the load value of the given system. We said that for a small change in the load value, we get the similar changes in the expression on the right hand side. We carried out the derivatives with respect to both the part with the A transpose as well as the S, and we got the two expressions. For the first expression, when we evaluated, we got the overall value of A transpose into ds. ds was adopted with the value of k naught A into du bar in the given system, which means that I am trying to connect this overall system in terms of the nodal displacement values of the given system. So, the intention is very clear that I want to get the relationship between dp bar and the du bar of the given system. So, as I substitute this expression, I get that this is the one part of the parameter into du bar plus the second expression, which we have still not worked out. Then what I realize that if the first part of the system is the dp bar, which is a force vector, the second part over here is the du bar, which is the displacement vector, then this parameter, which is the multiplier of it, should be the stiffness of the given system, and that is where we identified that this is the overall stiffness, a 4 cross 4 matrix of the given system. When I open this up, we get these two parameters in the given system, and now if you recall, k naught, if I just substitute the value, comes out as AE upon L in the given case, and this is nothing but this is the linear stiffness which we have been following up to now for any given truss problem. So, if you have a truss problem identified and you locate the for the given member of the truss which were defined in the local member coordinate, say x of m, y of m, and at this position we have defined these degrees of freedom in the given system, we locate this as a standard stiffness matrix for the given system. What we have got as the second part is the contribution of the nonlinear stiffness of the given system, but this nonlinear contribution has typically been provided by the large displacement terms. So, I will call it as k of a n in the given problem, which means that it is included due to the parameter of a in the given problem. And if you look at this parameter, this is all the function of phi, which is V2 bar minus V1 bar upon L, which means that this whole parameter of the given system is a function of the displacement, it is not a constant value. So, as the displacement of the system will modify, this parameter of the stiffness k of a n will also modify itself, and that is where the nonlinearity has been introduced in the given problem. Okay. So, this is corresponding to the first part. Now, I can go ahead with the second part. So, this is what we have written, that the overall k of a which we got in the system is written as the first part, which is the linear stiffness, and the second part, which is the nonlinear combination of the system. So, I think I will just correct, I will just write it as k of n delta in the given problem with the bar symbols in the given system. So, the first one, which is the linear stiffness, and the second one, which is the nonlinear contribution in the given system, they both have been identified. Now I can go ahead with the second term which we didn't take up to now. So the second term is dA transpose into S. As I adopt this parameter, I write it as the dA transpose into S, which is now contributed with respect to the given displacements in this given expression which we defined earlier. So it can be written as K naught, or I can rather say that d of A transpose into S. S can be written in the same manner as we have defined earlier in the given system. So I will just try to express that what is the dA transpose in the given problem. So as the value of A for the given problem is written, it is minus of 1, minus of phi, 1 and phi in the given system. This value is defined with respect to the parameter phi, where phi itself is defined as V2 bar minus V1 bar upon L in the given system. So if I now take a small variation in this parameter, so d of A, it will identify itself as the first parameter with respect to the 1, there will be no small fraction in it, so it will come out to be 0. For the second parameter, if I take it, it will come out as d of V2 bar minus d of V1 bar upon L in the given problem, and this all will be coming with the negative sign because this is minus of phi. So that is what has been defined in the given system. The third parameter, which is again 1, a constant value, so no variation in that. The fourth value, which is again phi, and again I got the value as d V2 bar minus d of V1 bar upon L in the given system. So now this becomes the standard d of A, the changes in the A vector of the given system. We identify it in this manner now, and now I can write the expression which is defined over here as dA transpose into S as the multiplier of this part, which is 0 minus of d V2 bar plus d of V1 bar upon L, 0 d of V2 bar minus d of V1 bar upon L multiplied by the parameter of the S. So this becomes a vertical vector, the column vector of the given system, multiplied by the S, which happens to be the member force of the given system. So if we keep the S value as a constant, we get the multiple cases of the standard buckling analysis of the given problem. We will just see briefly that what this overall term depict in the given system. But as a given process, now if I have written the expression in this manner, I will try to consider this expression also in the similar manner as we did with the previous problem. So we want to express this all expression, as if you recall that our intention is that we want to express that dP bar should be written as a function of as some multiplier into du bar in the given system. So I eventually want to get from this expression also somewhere the du bar multiplier. So in order to get the du bar multiplier from the system, what I will get, I will write the given system such that the overall parameter is written as it is, and I multiply it with respect to du bar, which is d of u1 bar, d of v1 bar, d of u2 bar and d of v2 bar in the given system. So this happens to be a 4 cross 4 matrix which I am considering, and this happens to be a 4 cross 1 vector. If I will multiply these two, of course this will give me, or this should give me the same vector which is 4 cross 1 in the given system. So my intention is to get some coefficients inside which will eventually give me the same vector, but I am able to get the du bar in the given system as a multiplier. So when I look at the first equation, I realize that it is 0. So all the multipliers with respect to du bar, du1 bar, dv1 bar, du2 bar or v2 bar, they should all be equal to 0. So the first row has all the parameters 0. So of course when you multiply these 4 with these 4, you will eventually get the value of 0, which is the first parameter over here. Now the second parameter which I want to get over here is this term. So if I want to get with the multiplier of du1 bar, I get that there is no coefficient over here of the du bar, so this is 0. du2 bar also no coefficient, so this is also 0. But with the dv1 bar and dv2 bar, we got the coefficients and we write them as s upon L and minus s upon L in the given problem. So if you now multiply these second row with the column vector, you will realize that this will eventually give you the same expression of dv2 bar plus d of v1 bar upon L into s in the given problem. So this is the expression which we initially started with, and that is what we have got, or we have obtained by this standard form. Now similarly I write the third one, which will again come out to be all 0, and the fourth one, if I realize, I will write it as minus of s upon L 0 s upon L in the given system. So what we have done, we have modified our second parameter also in a simplistic form, where we have got one part of the expression of a 4 cross 4 matrix, and that is now multiplied by the du bar in the given system. So what eventually we get from here is d of A transpose into S is equal to some stiffness related part into du bar. Why did I call it as again a stiffness related part? Because we have been writing the equation of the force in terms of the displacement related parameter. So whatever is the multiplier of this displacement term, that has to be the contribution of the stiffness or the equivalent stiffness of the given system. But as this is the not a regular stiffness of the system, so I call it as K of G in the given problem, and now we consider that this is the geometrical stiffness of the given problem. So we'll talk about that, what is the physical significance of these individual terms, but what we have now eventually got from the overall system, we identified that this overall term, which is written over here, is the geometrical stiffness contribution of the system, and once I now substitute it in the given equation, I can write the system of the dP bar is equal to K of A bar into du bar plus K of G bar. I will better put here also bar, because this is also in the local member coordinate, into du bar in the given system, and this gives us that this is the geometrical stiffness of the given system. Whereas this K of A is containing two parameters, one which is K naught of the given system, which is the linear part, and the second which is the nonlinear part of the given system, and these two parameters of the system have been already evaluated for the given parameter. So what we realize now in terms of the individual contribution, the first one, which is the K naught or K naught bar, is the linear stiffness of the given system. So as we look at the general system, this comes out as a simple function which is in terms of the constant values, and that is what the linear stiffness of the given system was. The second parameter is the contribution of the stiffness due to the nonlinear or the large deformation parts, and this eventually comes out as a function of the phi parameter of the given system. So we have all the changes which are taking place in the system due to large deformation, those all will be contributed in the stiffness through this particular parameter in the system. So as the displacement changes or gets modified, the stiffness of the system also gets modified due to this parameter of the nonlinear stiffness part. At the same time, we now got a term which is the geometrical stiffness in the system, and if I look at the expression, it comes out in this manner. So it is defined in terms of the S upon L parameter of the given system. Now what this parameter identify, S is the member force which is active in the given system. So as we have some internal tension or compression forces in the given system, we understand now that due to these internal member forces which are active in the system, the stiffness of the system also gets modified, and this brings the very important point in the whole discussion, that the stiffness of the system is not only getting modified due to the large displacements which are taking place in the system, but the stiffness is also getting modified due to the forces which are active in the given system, and once these large deformations are active, these forces are also modifying the stiffness of the given system. So if you consider that this is a member, as I am applying some kind of a internal member force, as long as the forces or the displacements are small, it is doing good, but the moment I say that the displacements of the systems are large, say the system bends into some form, if I consider a very simple example that the system modifies into some bent shape, now at any point the compression load which is active in the given system is also trying to put the geometry such that the compression load is going to make the internal member deform. So this internal member force which is active in the system is also now responsible for the change in the stiffness of the given system. In the initial case, when I was applying the load as a simple case, I simply considered that the load is constant, and with respect to the given load, the system is experiencing some displacement. But as the system undergoes with the large deformations, due to the large deformations, already one contribution of the stiffness modifier is there, or the stiffness is being modified, but at the same time now the compression load which is active on the system is also modifying the stiffness of the given system, and this is what we identify by the geometrical stiffness term of the given problem. So, we consider here now that the linear stiffness is the first parameter which we define as the k naught, whereas k of n delta, which was the nonlinear contribution due to displacement, and the second k of g, these are the two contributions primarily which are all introduced due to these large deformation problem. So, once we introduce the large deformation in the given system, there is one contribution of the nonlinear changes which are in the stiffness matrix, and the second which is the changes in the stiffness matrix due to the internally active forces of the given system. And here we also bring the second idea that if the force is tensile, maybe the stiffness of the system could be enhanced. At the same time, if the force is compressive, the stiffness of the system could be decreased, and this manner the behavior of the geometrical stiffness could be adopted in both the ways. It could either modify the stiffness in a positive manner, or it can decrease the stiffness in a negative manner for the given system. So, with this idea we understand now that the overall matrix which we define for the system is called as a tangent matrix. We define it as the sum of the linear stiffness of the given system, the nonlinear stiffness with respect to the delta deformations in the given system, and the geometrical stiffness of the given system. So, using this overall idea, we realize that the expression can be written as dp bar is equal to k naught bar plus k of n delta bar plus k of g, which is the geometrical stiffness term, into d of u bar in the given system, and the sum of the all these three stiffnesses is the kt, or the tangent stiffness matrix of the given system. We are putting the bar on top of everything because we are knowing that all these derivations are done in the member local coordinates, and that is where we define this parameter in also in the local member coordinates. So, this is the tangent stiffness matrix, and this describes the overall stiffness of the given system. So, once we summarize the overall process, we realize that the dp bar was written in terms of two parameters. We modified the expressions for the given system, and we realized that the dp bar can be represented as the idea of dA transpose and the k of a bar kg bar in the given system. K of a has also the two components. I will just put the bar on top of it, which is the k of linear or k naught in the given system and k of nonlinear in the given problem, and using now these two terms we get the overall tangent stiffness of the given system. So, this is the tangent stiffness which we typically describe. Now, as a simple measure, we have described these relationship, which is the k naught bar, this is the k of n delta bar in the given system, and this is the k of g bar in the given system. So, the sum of all these three is the actual tangent stiffness matrix of the given system. Now, why we call it as a tangent stiffness matrix? As a simple analysis, one can understand that the p bar, when we write it in terms of the A transpose into S, this as an expression, we understand that A transpose is already given as a function of displacement. S can also be represented as a function of displacement of the given system. So, this overall equation is a generalized expression which is defined in terms of the nodal displacements of the given problem. So, if the overall forces or the nodal forces of the system are expressed already in terms of the nodal displacements, we can simply define it as that the change in this parameter with respect to these nodal displacements will be written as the del f upon, so I can write it not as a partial derivative, but dp bar upon du bar can be written as the standard value of the derivative with the system and with respect to the nodal displacements of the given system. So, if this parameter is identified, at any point we can consider that d of p bar is equal to del f upon del u bar into du bar in the given system. As a generalized expression, I can bring the relationship in this manner. So, what we understand that the function which is describing the relationship A transpose S, if I just try to draw this function on the given system, so the parameter of the kt is evaluating the tangent on this given system with respect to a variation in the u bar parameters of the given system. So, if p and u changes along the two axes, the function which is defined by this A transpose S expression is drawn by some form over here, then this kT is nothing but the tangent on the given system at the respective points, and that is the reason why we typically identify it as a tangent stiffness of the given system. So, this is the total stiffness contribution which is added in the given problem, and we have already seen that this is defined in the local member coordinates. Now, in order to do the conversion from the local coordinate to the member generalized coordinates, we understand that at a given system this is the global x coordinate, this is the member which was defined in the local coordinate of the given system. So, if I want to now convert from here to the global coordinate of the system, I can make a transition by x of m, y of m in terms of the standard transformation or the rotation matrix which we define, cos alpha, sin alpha, minus sin alpha and cos alpha. So, with this idea we are able to make the transition between the member coordinates to the global coordinates of the given system. And now, using the similar idea, we can modify the overall stiffness of the system. So, the kT bar which is defined in the local member coordinates can also be modified in terms of the overall structural system or the general kT expression of the system, by considering that if I adopt that this parameter is rotation matrix R in the given problem. So, we can write this now as kT will be equal to R transpose kT bar into R into R. So, this is the standard expression which we have been using earlier in the course for the stiffness evaluation in the global coordinates of the given system. We again utilize the same expression. Over here also R happens to be a standard matrix of the size 2 cross 2, because right now we have only 2 degrees of freedom of the given system, and corresponding to that the values which are not defined here and which are the null values, they are actually the 2 cross 2 null matrices of the given system. So, with this idea we are able to now convert the standard tangent stiffness matrix from the global coordinates to the local coordinates of the given system. In number of situations we may be required not to take the overall stiffness part, but only a part of it, and that can also be done only partially by taking the requisite amount of multiplier. We will briefly see that in one of the example problems. With this we stop over here. We have briefly seen that what is the overall implementation of the geometrical nonlinear analysis for a plane truss members. This contribution is added with respect to the rotation term, and then also we have a simple member axial force which is active in the system and which also modifies the stiffness, and accordingly we define them as a nonlinear stiffness contribution and the geometrical nonlinear stiffness contribution of the given system. Now, this is the procedure which we have identified, and we will later see that how the stiffening and the softening effect can also lead to the general buckling in the given problem. With this we stop over here. Thank you everyone.